Okay, so today our speaker is Hariharan Narayanan, who is a faculty member in the School of Technology and Computer Science at TIFR in Mumbai, and he's going to talk about spectrum of sums of random matrices and connection with hives. So, Hari.
Thank you, Piyush and Savya, for the kind invitation. So I'm going to talk about large deviations for random hives and the spectrum of the sum of two random matrices. This is joint work with Scott Sheffield. So I'm going to spend a lot of time on this slide. This slide gives a polyhedral way of looking at the distribution of the sum of the spectrum of the sum of two random Hermitian matrices with given fixed spectra, whereby random I mean uniformly random from the natural volume measure. So on the one hand, we have two random matrices X and Y, or Xn and Yn if you want to index with the number of the dimension, and these have fixed spectra which will be approximating some curve, and we are looking at the spectrum of the sum, and we wish to understand the distribution of the spectrum of this sum. Okay, so that's the high level picture, so this picture that you see around over here, it gives a polyhedral way of looking at the distribution of the spectrum of the sum of X and Y. What is the now I'll tell you exactly how that comes about. So I'm going to now suppose for this slide that X has spectrum 15, 5, -5, -15, and as you see, if you start from 0, these are the increments while going up. So 0, 15, 5, -5, -15. And now similarly, I'm going to assume the spectrum of Y is the same, so it goes up by 15, goes up by 5, goes up by -5, goes up by -15. Okay, the bottom row is always 0. So this is the boundary conditions of some array. The vertical left column represents the spectrum of X. The horizontal top column represents the spectrum of Y. And now what is above this pink diagonal?
Sorry. So you said the spectrum was something, and then you derived this going up and down from the spectrums. Can you repeat that again?
Yeah. So if you first add 15 to 0, you get 15. Then
you
add 5.
First of all, the spectrum of the first matrix consists of 3 points on the real line, 4 points on the real line. What?
So it's got 4 numbers: 15, 5, -5, -15.
15,
they correspond to the slopes on this vertical line here. So I'm going to. So I have written these numbers on these lattice points.
Okay.
I'm really going to be looking at a piecewise linear extension of this to a concave function on the entire vertical line.
Okay.
So that's how. And similarly, I'm going to look at a piecewise linear extension of this to the horizontal top.
Just one question.
Yeah.
You see, the spectrum is not ordered. So how are you ordering when you take the sums and so on?
Oh, so what do you mean spectrum is not altered?
You see, spectrum of a matrix is a set of numbers, right?
Yes.
With multiplicities.
Yes.
Right? So how are you going to add if I want to do it, you see?
No, but these are random, they're conjugated by Haar random unitaries and then added.
No, that is not BB's question. BB's question is actually mine also. How do you get how do you get these numbers on the vertical axis from the spectrum? And okay, let me say something. And so you think of the spectrum as atomic measures concentrated at 4 points, and then you just look at the characteristic function of this measure, namely integrating from -infinity. So you get these step functions. First, is that?
Yeah, you get the step functions, but those step functions are the slopes. So I want a concave function, continuous concave function in the end.
No, okay.
The question is probably that why not 15 minus 5, 5 minus 15, or why not start with minus 15? So
this is a convention. I'm going to start at 0 at the left bottom corner, and then I keep adding the partial sums of the spectrum. So I first add 15, then I add 5, then I add minus 5, then I add minus 15.
No, but my question is, you said you will first add 15.
Yeah.
How did you order the spectrum in 15, 5 minus 5, 15? Why not 5 minus 5, 15?
Oh, that way. It has to be in decreasing order. I'm sorry. It has to be in non-increasing order.
Okay, thank you.
Yeah,
Okay.
Sorry, I should have said that. It has to be non-increasing order. Yeah, I should have said that. I'm very sorry. Yeah. So it's a non-increasing order. Here also non-increasing order. And now we have these rhombus inequalities, which in our setting are really parallelogram inequalities. So for every square like this, the sum of the entries on the marked diagonal has to be greater or equal to the sum of the entries on the unmarked diagonal. And similarly, for every parallelogram like this, the sum of the entries on the marked diagonal has to be greater or equal to the sum of the entries on the unmarked diagonal. And there's a third kind of parallelogram, this kind, the same condition. Sum of the entries on the marked diagonal greater or equal to sum of the entries on the unmarked diagonal. So these are called rhombus inequalities in the notation of Knudsen and Tau, who introduced this in their proof of the saturation conjecture in representations here. Now, so these are the inequalities that define a hive in the part above the pink diagonal. In the part below the pink diagonal, we require all of these inequalities except for the ones for squares. So for example, for this square, I don't require the sum of the entries of this diagonal, which is 10 plus 15. This is not greater or equal to 20 plus 7. So that is not required below the pink diagonal. Above the pink diagonal, there are 3 varieties of inequalities for the 3 kinds of parallelograms. Below the pink diagonal, there are only 2 for the 2 parallelograms. There is no condition for squares. So we call this an augmented hive. And essentially due to the work of Knudsen and Tau, it follows that if I pick a random point from this polytope and I just note the values on the lattice points on the pink diagonal, and I take the slopes in the same way that I've been taking the slopes so far, I will get a vector which has exactly the right distribution, namely the distribution of the spectrum of the sum of x and y. So this follows from the work of Knudsen and Tau. So what we want to do in this talk is we want to make the spacing tend to 0. So we'll have some concave functions about here and here, and then we let the spacing tend to 0 and look at the distribution of random functions that we get on this pink diagonal, which are obtained by piecewise linear extension of the lattice points in each case. Okay, so that is the goal. Are there any further questions?
So just to clarify, so you said there's a unique solution to, so there might be many such assignment of numbers inside even given.
Yes, it's a polytope. So we're picking a random point in the polytope.
Yeah.
Which corresponds to one particular array of numbers, and then we are doing all this, and this whole procedure will give out one particular set of candidate spectrum, but that thing has the right distribution.
And the candidate is the entries on the diagonal.
That's right. The entries on the diagonal give the cumulative sums.
Yeah, and then you just do the successive differences.
Yeah. Okay, thank you. Okay, so now I'll introduce the setting for large deviations. So let Pn be the sequence of Borel probability measures on L infinity 0, 1. Here L infinity 0, 1 is really going to be the set of functions on that pink diagonal. So that pink diagonal represents the interval 0, 1. We're looking at functions on that, bounded functions on that, and supported on Lipschitz concave functions that are 0 at the endpoints, as we saw. So these functions are all 0 at the endpoints on the pink diagonal, defined by piecewise linear extensions. By the way, the 0 at the endpoints is only if the matrices are 0 trace. If you have a non-zero trace, you can have non-zero at the endpoint. It is not crucial. I've just assumed that without loss of generality here, because removing the trace doesn't change anything. So where xn and yn are independent Haar random with spec xn equal to lambda n and spec yn equal to mu n. Okay. So here is some initial things I need. So let lambda and mu. So lambda and mu are these surrogates for the eigenvalues. These are strongly decreasing. What that means is, their cumulative integral that you get, that is strongly concave. Basically, it means that there is some convex parabola I can add to it, and I can continue to get something concave. That's what it means. That's what strongly means. So strongly decreasing, bounded on 0, 1, integrates to 0. And these lambda n are the slopes on these intervals I1, I minus 1 by n to I by n that we saw already. So lambda n I is n times integral I minus 1 by n to I by n lambda. Similarly, mu n is the slope on one of these pieces from I minus 1 by n to I by n. Sigma s is minus log f of s. This I have not yet defined. I will define later. F of s is actually going to be the volume of a certain polytope raised to 1 by n squared roughly, where the polytope itself is n squared dimensional. S is going to be representative of the average Hessian. But this I will describe later. V lambda is a continuous analog of the Vandermonde determinant. So if you just look at this, the discretization, you get something like a Vandermonde determinant. So this is important. So the rate function I at gamma. So this tells you how the asymptotics of the large deviation principle behave, where d gamma now is nu. So gamma is actually this concave function, and nu is the spectrum or on the pink diagonal. It's given by I gamma equal to log of this non-interaction term. Tau is some quadratic parabola, plus this is the infimum over all hives. So these however are continuum hives on the upper triangle. Lambda, mu, and nu are these continuous concave functions. And what do we mean by continuum hives? Basically, all the rhombus inequalities have to be satisfied at every scale in the interior of this triangle. And you take the integral of sigma of the Hessian of H. Now H doesn't have to be C2. It can be just Lipschitz concave. But nonetheless, because it's Lipschitz, the Hessian is known to be a radon measure, and it can be decomposed into an L1 part and a singular part. And the singular part will not matter in this integral. The L1 part can be evaluated because sigma satisfies suitable properties. Okay, it grows very slowly, logarithmically, basically. That is what we need. So this is the main theorem. The main theorem is if you have this rate function, which I've taken to be n squared by 2, you could take it to be n squared, that's fine. As long as you correct it for it later. So for every Borel measurable set E in L infinity 0, 1, so what we're doing is we're taking some subset of the possible concave functions that you can get on this pink diagonal. These are continuum concave functions, and we are asking what is the likelihood at scale at iteration n, where n is this the discretization level. What is the likelihood that my random spectrum coming from the sum of two matrices lies inside this set E? So we have first embedded some sort of polytope. It's a finite dimensional polytope for every finite n. We've embedded this finite dimensional polytope into L infinity 0, 1 by taking piecewise linear concave extensions. And then for this fixed set in L infinity 0, 1, we keep asking what is the likelihood that when I pick a random point in this polytope and look at the points on the pink diagonal, that the resulting piecewise linear concave function belongs to this set. So that is what Pn of E is at the nth level. These Pn are the measures corresponding to different n. You take the log, scale it, and look at the lim-inf and lim-sub. And the large deviation principle says that this belongs to a certain interval. On the left, it is inf gamma belongs to the interior of E I gamma. On the right, it is negative inf gamma belongs to closure of E I gamma. So this is the general form of a large deviation principle. However, in some special cases, the two endpoints can agree, and then you get equalities everywhere. So I want to discuss just for some, this is not really important, but this was the original setting of Knudsen and Tau. So they have these equilateral triangles which they break up and create hives of, and so on. And this is why they were called rhombus inequalities, as you see, because now indeed all the parallelograms look like rhombi. I had distorted one of them to make it a right triangle, then one of them becomes a square, the other two are parallelograms. But the original setting was this. So this is why they are called rhombus inequalities. So I'll now introduce the term discrete Hessian. So the discrete Hessian is a map from the unit rhombi to the reals. And as you see, I've labeled them A, B, C, D, and the discrete Hessian is always simply B plus D minus A minus C, where B and D are on the long diagonal and A and C are on the short diagonal. Okay, and now let's look at the.
So your condition was that this B plus D minus A minus C should always be negative or non-positive.
Yes, it should always be non-positive, and because I'm working with concave functions, I chose this sign convention because I want it to be concave. Yeah, so in representation theory, this is a Littlewood-Richardson coefficient, and this particular gadget was introduced by Knudsen and Tau in order to prove the saturation conjecture, which is that basically if for some, when I multiply nu lambda and nu by some k, if this coefficient is non-zero, then it has to be non-zero even without the k. That's what the saturation conjecture is. So they completely transformed it into a problem in polyhedral geometry, and then they proved it, in fact, using linear programming. They proved that when you do linear programming on a certain polytope, you get a vertex which is integral, and that certified that this coefficient is non-zero. So yeah, so it's a very polyhedral proof. So this is what they. This is the context in which this Littlewood-Richardson coefficient is defined. I guess in this talk, it's more important for me to describe the connection to statistical physics. So I'm going to spend some time now describing the connection to tilings. So these hives, they form concave surfaces. Out of this picture, you see, I can also form a convex surface by associating with every face that you see here, a face of some surface that kind of moves upward. So every time you see a line here, it moves upward. And this surface is essentially a Legendre dual of the hive. But another way of putting it is what I'll just say now. So if I associate with every point here in R2, I identify that with the gradient of a face. So here, for example, is a concave function, and there's a gradient here. It's in an R2. Here also there's a gradient in R2. But the difference between these two gradients is going to be perpendicular to this line, because these faces they agree on this line. Because it's a continuous function. So that condition being perpendicular to this horizontal gives rise to a vertical line here. And similarly, it forces all these honeycombs to have the right angles. It doesn't say anything about the lengths, but it forces the orientations to be exactly right. So this is a random honeycomb where the semi-infinite lines here are fixed. But the vertices are not fixed. The vertices here correspond to faces in the hive. Okay, so you just fix the semi-infinite lines to try to construct a hive at random and ask what is its geometry. So this is intimately linked with the geometry of a random hive with some fixed boundary conditions. And there is what I just said was a sort of a real analog, but there's an integer analog of this question as well, that comes from Littlewood-Richardson coefficients, which incidentally count the number of integer points in these hive polytopes, the part above the pink diagonal, rather than the volume, which is what appears in the random matrix story. So here you have this mosaic. It's called mosaic by Kevin Purbu. It's they're fixed, made of squares and triangles. And on the right, you have puzzles. These are introduced by Knudsen and Tao. And here we have a sort of a square triangle tiling. These are also, I believe, introduced by. I mean, this connection is from Kevin Purbu's paper called Puzzles, Tableau, and Mosaics. And here, these are actually thickened honeycombs. You thicken the honeycombs and you turn them into little squares, and then you turn them into, you have these little triangles, and actually this part is also filled by little triangles. And now this is in bijection with the so-called LR skew tableau. So this is what you see here, the so-called LR skew tableau. It's a tableau with certain constraints, and this is nicely color-coded. This is actually from Kevin Purbu's paper. It's nicely color-coded, so you see what's the correspondence. So here is another example of giving height functions. So here you have a tiling of a trapezoid where here you have these slight serrations, and you are coloring them with yellow tiles, green tiles, and red tiles. And as you see a surface. I mean, and that surface can be encoded using some sort of stepping rules with certain colors. You know, you increase or decrement your surface. So in this way, instead of studying a random tiling, you can study a random surface. And this is the connection to the height functions. So here I'm reiterating the connection to random matrices, and the volume of the polytope. This is specifically stated in paper of Knudsen and Tao. The volume of the polytope P lambda and mu and un above the pink diagonal, all the values, that's a polytope of all real hives, is equal up to known multiplicative factors involving Vandermonde determinants. These Vandermonde determinants are the weighting factors that come from the part below the diagonal. To the probability density of obtaining a Hermitian matrix with spectrum nu n, when two independent Haar random Hermitian matrices with spectrum lambda n and mu n are added. So what we want to do now is to look at these hives when the n is extremely large, and when the n is extremely large, if you focus on a very small region, it tends to sort of look kind of quadratic, because of Alexandrov's theorem. It says that a concave function is twice differentiable almost everywhere. There may be some conditions, but all those conditions are met here. I mean, maybe, so what we're doing is we're going to consider a polytope of mean zero functions on this discrete torus. So why are we looking at mean zero semi-concave functions? The thing is, we wanted to look at these quadratic functions with the average Hessian. Now what we instead do is we look at quadratic functions which are with a periodic Hessian with period n, and with a certain average value. And we look at this by first taking these functions and adding a convex quadratic of the right Hessian, so that now these, instead of being random concave functions, they become random semi-concave functions, which are actually periodic rather than simply having a periodic Hessian. Now these are actually periodic, so you can view them instead as functions on a torus. So what we care about here are random semi-concave functions which are mean zero on a torus. This is the torus, such that the discrete Hessians are dominated by S equal to S0, S1, S2. This is the polytope of dimension n squared minus 1. Okay, so you get this polytope. So what is the volume of Pn of S? So suppose S is equal to S0, S1, S2, 2 is equal to S0 lesser equal to S1 lesser equal to S2. We see that the mean zero function of the discrete torus taking values in minus half and half completely belongs to Pn of S. Why? Because the Hessian will always be dominated above by 2, and 2 is equal to S0 here. Okay, so this implies that we get a lower bound on the volume of the polytope I just said of 1, because result of Wallard says that a central cross section of the unit cube, that we need to take a section because we're talking about 0 mean sections. Therefore, Pn of S is greater or equal to 1. So we got a lower bound. The marginals of the log concave densities are log concave as a consequence of the Prokopy-Lindner inequality. And using differential entropy, we can show that the lim sup of Pn of S to the 1 by n squared minus 1 is also less or equal to 2e. So this is an upper bound. How does this upper bound come about? So basically, you take a random point in this polytope Pn and you look at one small square. When you look at one small square, of course, you get some, it bends upwards or downwards, depending on how the Hessian goes, the Hessian on the square. And but however, it is the distribution of that particular linear function on the polytope that evaluates just the Hessian on one square is log concave by the consequence of Prokopy-Lindner. However, it is bounded above by, let's say, 2 by the semi-concavity constraint that we have enforced. Therefore, it's a log concave. It's also mean 0 because we are looking at mean 0 sections, and all the squares are identical. So you have the 0 mean for each particular squares, the distribution. So we have a distribution that is bounded above by 2, is log concave, and is mean 0. It turns out that such a distribution cannot have a large entropy because it just forces the tail. It cannot be too wide because basically the mean is forced at 0 and you're not allowing it to go beyond 2. So it just simply doesn't have space to expand much, and it ends up having small entropy. And this gives us an upper bound. So together we get a lower bound and an upper bound on the volume of Pn of S. And one can also show that it is approximately monotonically increasing, again using the same kinds of tools. And this tells us that the limit of Pn of S to the 1 by n squared minus 1 actually exists and belongs to 1, 2e. Okay, so and additionally we prove some rates. So we can show that Fn of S is less or equal is bounded below, above and below by these things, and these things are tending to a fixed number f of S at a certain relatively fast rate. So now I want to talk about some of the tools used in our analysis. So I'll start with the Brun-Minkowski inequality in convex geometry. So suppose you have two convex sets, this green convex set and this blue convex set. Then the Minkowski sum is obtained by just shifting that green convex set all around. So its center is moving all over the blue convex set, and see what area is mapped out. That is the Minkowski sum. Another way of saying this is the Minkowski sum of the set K and L is the set of all points such that it has the form V plus W, where V belongs to K and W belongs to L. So that's what the Minkowski sum is. And the Brun-Minkowski inequality states that the volume of K plus L to the 1 by M is greater or equal to volume of K to the 1 by M plus volume of L to the 1 by M. So this is what the Brun-Minkowski inequality states. In the periodic case, by the Brun-Minkowski inequality, the volumes of these parallel d-dimensional sections of a convex body raised to d inverse define a concave function. So for example, here the two convex bodies are this triangle on the left, and this triangle on the right. And we have some convex body, not necessarily the convex hull of these two. We have some convex body that contains these two triangles. But at the extreme points, these are the intersections of the convex body with some affine subspaces. If you shift these affine subspaces, you get these other convex bodies, such as this one. What it turns out that this convex body will always contain the Minkowski average of the leftmost convex body and the rightmost convex body, simply because it contains all the points you can get by joining lines, one point in this and 1 point in this, and that will correspond to the Minkowski average. Okay. So consequently, Fn of S is this is the same. This is the reason that Pn of S is to the 1 by n squared minus 1 is a concave function, because actually so this suppose for example this is Pn of S prime, and this is Pn of S double prime. Then what happens is if I take the Minkowski average of these two, the polytope here will contain these two, the Minkowski average, and hence be concave because of Grun-Minkowski inequality. So that's essentially why this Fn of S is a concave function of S. Okay, so next let's let me give you the proof idea of the large deviation principle. So the whole idea is we need to take these hives, break them up into tiny squares, and on each square somehow identify them with some parabolic surfaces, and then patch together in some fashion and get all these things that we get, because we call that the rate function itself was the integral over sigma of the Hessian. So the idea is that you somehow break things up into small squares, and on each square this Hessian is almost constant, and you write it out and then get basically what you want. So we're going to partition into small squares. We're going to have actually 4 or 5 layer boundaries, although in the picture I've written double layer boundaries. Why is this? What we want to do is we want to just fix the values on the boundary and then look at random hives conditional on these boundary conditions. When you have that, what happens in one piece here is completely independent of what happens in another piece here. The reason is that all the rhombuses which go from one side to another, they cannot cross from the interior of one of these into the interior of the other. They'll get stuck in the boundary because the boundary is very thick. It's 4 or 5 layers. These rhombi have small diameter. Okay, so what this means is that I just described a polytope, which is the polytope where all these boundaries are fixed to something. That polytope is actually a product polytope of a lot of polytopes on these little squares, and they completely don't interact at all. So now we'll upper bound the volume of such a polytope. How are we going to upper bound it? So we look at the dyadic. We'll look at this dyadic square with a 4-layer boundary. We're going to use the Grun-Minkowski to upper bound the volume on one of these pieces. Now the difficulty here is that here we have fixed the boundary, but we have not fixed the boundary exactly to quadratic boundary conditions. If that were the case, then it would be quickly we would say that it's a subset of a Pn of S, and we would get some bound. But it is not. It can be some other boundary conditions which are different from quadratic. So what we do is we, however, know that it has one extension. Otherwise, we are not interested in these boundary conditions. It has one extension. We will take that extension, subtract it from this picture, and then get a semi-concave function, semi-concave constraints inside with 0 boundary conditions on the surface, on the boundary of this red thing. So we have semi-concave constraints inside, 0 boundary conditions outside. And as a result, we have to get an upper bound on polytopes of this sort. So this can be done using the Grun-Minkowski inequality. So what we do is we view these, because we now have 0 boundary conditions on the sides, we can view them as functions on a torus, because they just pass together so seamlessly that they can be viewed as semi-concave functions on a torus, where no doubt there are some bands where they are essentially fixed to 0, but we'll not worry about that for now. And because of this, you essentially need to get an upper bound on the volume of the space of semi-concave functions with different upper bounds on the Hessian at different points now, not constant upper bound anymore, because what we subtracted here is not a parabolic function, it's some other function. So we have non-constant upper bound. Nonetheless, this can be done using the Grun-Minkowski inequality. What we do is you take the torus and kind of translate the torus, or if you prefer, rotate the torus. I don't know what the right terminology is. I guess you translate it. But in terms of the function class, the polytope of functions, that polytope of function is getting rotated in some high dimensional space. But they all have the same volume, of course, because it's just a change in coordinates. You take the Minkowski average of all of these polytopes. That polytope will be contained inside Pn1 of S, where Si satisfies these conditions. And so we get an inequality. So we can actually upper bound the volume of this Qn1 of T, where T has this varying upper bound on the Hessian using Pn1 of S. And this is how we get the upper bound. So this Qn1 of T, let's say equal to Pn1 of S, and this gives an upper bound. Because we already know that this Pn1 of S as n tends to infinity, when you raise it to 1 by n squared, etc., you get a fixed function f of S. Now let's look at the lower bound. For the lower bound, we use something called a result of Fradolisi. Fradolisi's theorem says that the value of a log concave density on Rn at its mean is at least e to the minus n times the density at any other point. So, so this gives, like, it says that basically the value of the mean is not so much less than the value of the mode. So how is that relevant here? So now let's suppose, so this is actually going to be used only with the quadratic boundary conditions now. So we have quadratic, let's suppose we have quadratic boundary conditions. We want to show that by imposing quadratic boundary conditions, we have not reduced the volume of the polytope much compared to Pn1 of S. So Pn1 of S is with periodic boundary conditions. There's no clamping at all. Now we are clamping to quadratic boundary conditions, which basically means clamping to 0 with a semi-concave, with semi-concavity constraints. So you clamp to 0 on the boundary. Inside you have semi-concavity constraints. You want to show that the volume of this is not significantly less than having periodic boundary conditions and semi-concavity constraints. So that is what this Fradolisi theorem allows you to do, because these 0 boundary conditions by symmetry are actually the mean at these points. So what we are doing here is we are just forcing the function to its mean at these points and claiming that the value of the log concave density at its mean is at least e to the minus n times the density at any other point. But there are n squared points here. So e to the minus n is very close to 1 if you're looking at things at a multiplicative scale of n squared. And that's what happens. So you basically get a very good bound, lower bound on the measure of these polytopes. So next, we have to assume that this hive is C3 after smoothing. So this is a technical thing, but in the lower bound, because you have this condition involving the interior of E in the large deviation principle, you can actually smooth. So we can actually convolve and get a C3 hive after smoothing. And I mean, there are some caveats, but we can. Yeah, and then we can. So why is C3 helpful? I just did something that works only for quadratic boundary conditions. But if you have C3 or even C2 with uniform, uniform modulus of continuity for the Hessian, then you know that. I mean uniform continuity of the Hessian, then you know that for all these points the Hessian is essentially the same. It is very little different. And so what you can do is you can basically add a C3 correction to a parabolic surface, and you can work with the parabolic surface. So the C3 is what in fact C2 with uniform continuity of Hessian is what is required. So now, so here are some definitions that I need for a large deviation principle for random hives. They are very similar to the ones I've already shown, so I won't maybe spend time on them. But we get like, so this is a large, lower bound in the same in the same large deviation spirit for C2 hives. But as you see, the conditions are not so clean. I mean, we say that you take a hive H star, and you want to understand what is the volume of random hives at scale n, very close to it. So here's the epsilon. And what you get is that this is actually greater or equal to the negative infimum over all C2 hives that are dominated by hives contained in an infinity ball of H star. So this is because our lower bound procedure essentially used the fact that it's a C2 function with a uniform continuous Hessian. So we have, anyway, we get this from that kind of technique. The upper bound involved Brun-Minkowski and did not require any regularity. So we get a cleaner upper bound for C0 hives in the same context. When lambda and mu are C1, then in fact we have a slight additional argument, and we get a large deviation principle that involves the same kind of object on either end. So here we have this kind of thing. So it's equality. So note that previously we had inequalities. Now we have an equality. And this is, I will show you now how this is done. So basically, one has to show that suppose these boundary conditions are C2. When I say lambda and mu are C1, I mean that the boundary conditions, which are the antiderivatives, are actually C2. I need to show that if I take the maximum entropy C0 function, a C0 hive, I can actually do very, very close if I just take the maximum entropy C2 functions. So this is not obvious because you may be that for some peculiar reason you get these very highly probable C0 functions, but they don't translate into anything C2. But this is not the case if the boundary is C2. So what happens is we look at suppose you give me a great C0 hive. I take the C0 hive on this and I interpolate it to the full thing. So I was supposed to put the hive here. Instead, what I do, I put the hive here. Okay, the C0 hive you gave me. And then I add constant. This is constant here, constant. This entire square is a constant. I adjust things so that here the gradient is 0 and the value is also 0. Here also a constant along horizontal lines. And then I convolve this picture with a small bump function. Okay, that is C2. And also I should say I initially make sure that the boundary is a little bit, you have a little bit of leeway. So I don't just put the C0 function here. I put the C0 function multiplied by 1 minus epsilon and then put it here. So I got a little bit of leeway in this process. And that leeway is enough for me to just make a correction because these boundaries are C2. If the boundaries are not C2, I can't make this correction. So this is how we get a very similar rate function and get a equality there in the previous slide. So now I'm just going to, I finished a bit early, but I'm going to just wrap up and I'm going to tell you again like what the main result is. So we're talking about a large deviation principle where the set E is some subset of L infinity 0, 1. It is we have a sequence of measures corresponding to piecewise linear interpolations of the on the pink diagonal, and these are like polytopes embedded in L infinity 0, 1. They have measures with them. So we have Pn form is the corresponding measure. So this family of measures, but we are interested in the asymptotics of Pn for every E applied to any E, and this is given by the large deviation principle. So this was the same notation that I've shown you before. So this is the large deviation principle that we have. I mean, the rate function applied to gamma, or for gamma belonging to the interior of E, negative of that, and the rate function belonging to the closure of E, negative of that infimum over I gamma. These are the two endpoints of this is a rate function. This is some rate that you have to incorporate, but this is the log of Pn of E, and here you have also log of Pn of E lim sup. Here we have lim inf. Okay, so these two quantities are contained inside this bound. And here is one question. So I mentioned in the beginning that for hives, we don't get equality in the upper and lower bound. So actually, in the same problem would have persisted in the sum of two random matrices spectrum, but somehow, because we have an explicit interpretation of the values on the pink diagonal in terms of the operators, you can get around it and you have some additional flexibility. So we don't have these two different values for the lower bound and the upper bound. But in the case where the boundaries, the boundary conditions are C2, there we don't have a different nature of different subscripts here. So upper and lower bound, even for hives. But in general for hives we do have this, and so the question is, could this inequality be turned to an equality? That is one question. And the second more basic question is, we would like to get a closed form expression for f of s, using which we would like to write down a PDE for the scaling limit of a random augmented hive with given boundary conditions along the lines of Cohen-Kenyon prop, a variational principle for domino tilings. Such a result would shed light on tilings, random matrices, and asymptotic representations. Thank you for your attention.
Any questions? So about another question. So about the distribution of the random matrices, you assumed essentially nothing.
So the individual distributions, they have to be uniform. So meaning you take the diagonal matrix and then you unitary, random unitaries from the Haar measure. Yes.
Okay.
The Hermitian matrix.
Yeah. Okay. So it's UD dagger or?
Yes.
But this hive thing will not work for something like some Gaussian unitary sample or something.
No, it works, but then the boundary will not be fixed. It'll be a random spectrum that comes from the GUE spectrum.
Here the whole point was that the lambda n and the mu n are fixed in advance, and then you are getting random matrices.
Yeah.
But you can ask the question even there, right? When the lambda and mu themselves are.
Yeah, definitely. And in fact, the answers are cleanest for GUE very often. That semicircle law and all those things. Yeah, the answers are cleanest for GUE. So, for example, if you take two GUEs, you get another GUE with a different parameter. Yeah.
But the hive thing will still hold, or with the
hold, but what is the shape is unclear. So the hive will hold. So we know what the pink diagonal will tell us. We just don't know what the other values are. You actually know what are the values on the lower triangle as well, because that comes from these random Gelfand-Sutton patterns, or the minors of a random GUE matrix actually. So they are also GUE. And so you get those values exactly. What you don't get is the part above the diagonal.
Okay. Any more questions? If not, then we can stop the recording.
Thank you very much.